Hey everybody! Ever wanted to run unconstrained models? Today you can, because we're talking about inertial relief analysis. It's a pretty common analysis, especially in aerospace industry, but also, I don't know, automotive for sure does it too. And yeah, first of all, I want to show you the model, the tutorial we're following, and now let's talk fondly about what is an inertial relief analysis. If you just Google inertial relief, you will see that's lots of times it's explained on wing structures. So just imagine you have this plane and you are the pilot and you're sitting in the plane and you're flying through the clouds. Everything is fine, everything is great, and then you suddenly I don't know the English word for that, but you just lose the lift. Yeah, just fall into this air hole. I don't know if that's a thing in English, but yeah, you just lose the lift and you go down, and then you gain the lift again. And what will the wings do? Right, they will bend up, and that's because you had this movement, and the movement is stopped, and your inertia wants to move on and on and on, but it will be stopped, and then you have this bending up of the wings. I don't know if that's the perfect example to describe inertial relief, but it is like if you have any type of object really, and you want to move this object in a certain direction, like with a rocket or so, you have a thrust force pushing that rocket up, and the force acting against that is the inertia force, or the inertia reaction force, you could say. And it's the, I don't know, first Newton law that nothing moves until pushed, yeah, and for every action there's a opposite reaction. I'm getting messed up with the theorems. I don't really know the numbers, but it doesn't matter in this case. It's just that you have an understanding. So for rockets, you have this thrusting vector, and this force has to be balanced out, at least in the beginning, with the inertia, and then it will set into a motion. But you can just determine the stresses and the forces and what not the strains when you just do the following thing. You have the input force, and then you calculate what opposite force you would want to act against that to be in equilibrium, and this is what you will be applying as a volume force, or gravity load, you could say, or think volumetric force, and then this whole model is balanced out. And this way you can get pretty complicated analysis scenarios. Just like, imagine you would have the plane again, you have the weight, you have the lift, you have maybe turning loads, you have the wind, whatnot. But with inertial release, you can just throw all those loads onto the model, and the model will almost figure itself out how to constrain itself, because you just have to maybe not, but maybe you have to specify where the point is where you want to sum up all those loads and balance those loads out, and that's basically it. So it's a pretty cool analysis, and yeah, just I will show some resources in this video also, what I found useful and valuable for this analysis, where you can also dig a little bit deeper into the topic if you want to. But let's start with the tutorial here. So this will be our model. Did I tell you that this is also used in topology optimization? Now you know. So if you have come across this model, you know it already and are familiar with it, which is a benefit. So let's start. Now we have set here a Optistruct profile Hyperworks session. We have elements, we have components, we have material, we have nodes, we have properties, and we have a title. Well, that's good to have. Now, first thing we want to do is to just create load collectors. All right, so first of all, we create a load collector called static loads. So in this load collector, the loads will be which the inertial relief analysis has to balance out later on. Then we create just another load collector, which is called SPCs. The tutorial tells you to do that. I'm not really sure, but because it also could be support, because in inertial relief you will not hold something completely in place, but rather you would just support it on different points, because you want to have that rigid motion available for it to calculate the forces to balance it out. So if you just constrain it completely, that would be just a simple finite element method calculation, static, linear, whatnot. So this would not be inertial relief. So that just that you keep that in mind. It's support, and we will see about that in a minute. So we have now created two load collectors. We have SPCs marked as the current one, so everything what we are doing now will go into this load collector. So this is perfect. So we want to just create our inertial relief supports. And just a disclaimer here, you would not have to if you choose an option differently than we are doing in the end. But I will talk about that in later, yeah. Now, you have this boundary conditions, and then you have constraints, and there's a button called inertial relief. So the only difference between those two is same panel, same everything. I will move myself out of the way so you can see what's happening down here. Yeah, constraint is SPC and inertial relief is support 1. So it's just a image, card image. Is it the card? The load type is changed. So the how you what you're defining here, this is changed here. So this is support 1. Support 1, if you want to know, is a defining determinate reaction decrease of freedom in a free body. And yeah, so here you can support your model, and in all non-checked degrees of freedom, it's free to move. Right? So yeah, we will just go with the tutorial and just start. That was a misclick. Now you can see here you have those 2 points where you maybe want to constrain it. Yes, you want. You will constrain it here. Yeah, it's a bit hard to see, but you see this point is selected now, and here all translational degrees of freedom are fixed, right? So it could rotate in any direction, but it cannot move in any direction, if that makes sense. No translation, just rotation. All right, the other one has all the free DOFs too, but the DOF 1 it has not. So here we would want this whole thing here, this log, to be able to translate into X direction. So we uncheck it here. Great, you can see it here. If you want to check, man, what did I select here? You can always go to here, and then you see the 2 and 3, those are the DOFs which are checked here. And 0 is 0 motion, right? So, but I think that's clear. Now we have another point which we can only see if we make our mesh transparent, like so. And then there is some RBE element here. You can see it. It's rather tiny, but yeah, I can see it. And in this case, that's the important thing. Where is it? Yeah, that was comical. Yeah, it's this point here. I hope you can see that in the video, but yeah, so here is this RBE element, and on the top you would want to constrain only DOF 3 translational. Yeah, so like this, translational set direction, that would be constrained here. And yeah, so those are the support cards, which helps the solver determining which rigid body motions are available and how to balance it out. So this is this one. And then we want to create the static loads. So this would be, speaking in the rocket image, this would be the thrust forces, which we want to balance out. And I said that, I think a bunch of times now. So I will stop that and just do what the tutorial tells me to. So here we want to apply some loads, and yeah, how convenient. Yeah, I did that before. So set direction 3 to the power of 5, and then we have the X direction as well, same node, and here it is 10, 1, 2, 3, 4, 5. All right, so this is wrong. Yeah, sorry, it's minus 10,000. Okay, Now we have the two forces, we have that, and now let's create a load step, because that's all we want to do now. So we have the forces, everything else is set up, and now we want to create a load step. All right, right click, create load step. Now the load step is linear static, so we can choose that. And now don't make the mistake to select SPC here. It's no SPC. So we just have the loads, static loads, and we have the support one, which are the SPCs. Yeah. Okay. This is all set, and now we want to trigger the analysis to be an inertia relief analysis. So this is important that you don't skip this step, because it will not work, I think. So with the control cards, yeah, bad habit. So analyze and run and control cards. Here it is. Now here you find the very well known control card param, which we will check. And then there is, oh, I'm doing that all the time. Now then there is INREL, inertial relief. Yeah, this one. And now there are 3 options, and that can, what? See that? That's nice. If you click on the right, now it works. In the middle, it does. Okay, so 3 options. 0 would be no inertial relief, just a statically constrained model with no rigid body motions, and just that. -1 is that what we are doing here. We are creating support 1 cards and telling the solver how to have those rigid body motions. And -2 would be a completely automatic way to determining the rigid body motions and whatnot, and the constraint and everything else. And for what it's worth, Nastran would like you to use -2. So this would be the recommended one. We will look now later on the differences between the two, but in the tutorial it says -1, because that's what we are doing here, and that's good. Now we're done. So we can just run the simulation by just clicking on Optistruct and selecting whatever, and I will just do that as a test, because I run the model a few times now, just to see if I did something wrong here, and being able to correct it, and also see for the output a little bit. So yeah, we'll just run the analysis, and you see here you have your displacement value, and it completed correctly. And I will just look at the output file shortly to show you if there's something there with masses or so the mass matrix or whatnot. And there isn't, because you would have to set that. So inertial relief information such as rigid body forces and accelerations can be printed to the out file by setting param print FACC. Should we do that? I think we should, just to see it. Bad habit again. Control cards, param. I forgot. See, I'm doing that all the time. Yeah, this one. Yeah, 1 seems good. Let's just run it again and see how this would behave. And while we're waiting, I want to show you a little bit of the things I have looked into. So support 1 card we talked about. Param INREL. So this is the parameter which triggers the inertial relief analysis. And you see here you have this -2, -1, and 0. So 0 requests that constraint analyze should be performed. Yeah, no support card. Or support card are like SPCs. And -1 is what we are doing here, requests that inertial relief be performed. Alright. Support and support 1 cards are required in the bulk data section to restrain rigid body motion. The total number of degrees of freedom specified on support and support 1 cards must be less than or equal to 6. And yeah, so this is a little bit of a thing. You can over-constrain your model and then it will throw you an error. And then you have -2, request inertial relief analysis without the need for support and support 1 entry. Yeah. By the way, I have to see. I think I forgot to. I think I have closed a tab I would rather not have closed. But we can see that in a minute. Yeah, I have it. Yeah, just for reference, because I reference that so often. And yeah, I looked into the, I would say it's an Astran documentation here again. And there you have a little bit more of a documentation about the -1 and how it's supposed to work. And here you also have this introduction, and there it also tells you that second method recommended is to set it to -2. I'm not sure if that's also what Hyperworks or Altair would require or recommend you to do. Not require, recommend. But default is 0. Yeah, default equals -2 for modal frequency response subcases. Yes, I'm not sure about that. I think so, but I'm not 100% sure. Yeah, so going back to the tutorial or the output, we can now look at. So this would be the out file with the inertial relief information. And there you can see the rigid body acceleration, rigid body forces. And I think that's about it. No mass elements. But you also, that's very important, I think, the reference point. Because there's quite a debate a little bit happened 7 years ago. But still, I think it may be now still a thing. I will show you that here somewhere. Where is it? Oh, did I close that too? No, here. So they were talking about how to define it and whatnot, and I think he also complained about a model which did not behave like it should, because the reference point was not at the center of gravity where he wanted it to be. And the question was, how can you define the reference point? And the reference point can be defined by just going at the param and then ref point, PNT. There you can just define it. But another thing was really interesting. Raul, if you see that, yeah, write me a mail. Would love to chat again a little bit. Yeah, you see that he tells you a little bit about the calculation method of the reference point if you don't set it specifically, right? So if you don't do that, then the X, Y, and Z locations will be the averages. So you just have every grid in the model and every X, Y, and Z coordinates, sum it all together and just divide it by the number of nodes, and you will see where this is. So this will match the center of gravity when there's a uniform mesh, but not if the mesh is random, right? So just keep that in mind. That could be a thing if you run into it. And then another thing I really liked was this video about here. So if you want to, yeah, give them a like and a comment and subscribe to them. Hey, I did not. So let's do that right now. Awesome channel. I also picked quite a bit from their description about the PSD analysis in the last video, so I highly recommend it. And yeah, he is killing it in this video, just describing how this works and how the different parameters are set and so. So yeah, definitely if you want to go a little bit deeper into this topic, check that out. And yeah, going back to the results. Now we have run the model, we have checked our out file, and there was some of the values for the inertial relief analysis when you enable this parameter. But now let's look at the analysis, and maybe that's also interesting to just see what happens if you would use -2. And I did that already. So what I did was I did go back to the load collector, load step definition, I'm blind. Load step, yeah. Going back to the load step and then just deselecting the support. So just deselecting and applying. Not the red X, that does not work. Yeah, so just run it as this one and had the control cards set to -2, and I compared those two with each other, and the result is this. Here, let me just explain to you what I have here. So on the left side, this is our base model. -1 support cards enabled. On the top you have displacement, on the bottom you have stress. On the right side you have the same model, but with -2 and no support cards in the load step. At the top displacement, at the bottom stress. And what's interesting is, if you just play it, you see that there are different kind of motions, because the displacement here is completely different as the lugs are not fixed into place. So they will move, and you have a different kind of displacement overall and also in magnitude. So this changes. But if you look at the stresses, they're the same, right? So if you just see here, they are the same. And that's the same thing, and I really cannot explain it in total what the different why that is, but I think you can find a little bit more about that in this video. So if you want that, check that out, or enlighten us in the comments. That would be also a great idea. But I think for this video, that's about it. I hope that helped. So if you wanted to do some inertial relief analysis, you can now. And yeah, if you have any questions, comments regarding these tutorials, just let me know. Put a comment in, write an email. If you like the video, please like, subscribe for sure. And yeah, I see you in the next video. Bye guys.